All right, let's dive into a really fascinating problem today. Think about any big system you use, your social media feed, an online bank, pretty much anything on the cloud. It's not one computer, it's a massive system spread across servers all over the world. So here's the question. How do you figure out its true state at any single moment? There's no global clock, no single shared memory to look at. It's a huge challenge.
And this is really the heart of the problem, isn't it? When something goes wrong, you can't just hit pause on the entire internet and inspect its memory. The whole idea of now gets incredibly slippery. You know, if a server in Tokyo records its state, and then a server in Dublin records its state just a millisecond later, what does that combined picture even mean? Is it a real state?
Yeah, the difference is just night and day. On your own laptop, everything marches to the beat of a single central clock. You can freeze it, and you get a perfect, crystal-clear snapshot of what it's doing. But in a distributed system, you have none of that. No shared clock, no shared memory, just a bunch of independent computers firing messages back and forth that all take time to arrive. The state is just fundamentally ambiguous.
To really see why this ambiguity is so dangerous, let's make it super concrete. Let's imagine a dead simple banking system. We've just got two accounts, account A and account B. And our job is to be able to audit this system, to check on the total amount of money at any given time.
Okay, so to start, let's say account A has $100 and account B has $100. The ground truth here is simple, right? There's a total of $200 in the system. That number should not change unless we're explicitly depositing or withdrawing money from the outside world. Now here's where things get messy. Account A sends $50 over to account B. But imagine we try to take our snapshot in a really clumsy way. We record account A's balance before it sends the money, back when it still has $100. But for account B, we're a little late. We record its balance after it receives the money, when it's already up to $150. And boom, our snapshot now shows a total of $250. We've literally created $50 out of thin air. This is what we call an inconsistent snapshot, and it's a classic problem. See what happened? We recorded the effect of the transfer, the money arriving, but we completely missed its cause, the money leaving. We've captured a state that never, ever actually existed. So how in the world do we fix this? Well, the solution starts with a really simple, intuitive idea about cause and effect. This quote just nails it. A valid picture of the world can't show an effect without also showing what caused it. The letter can't just magically appear in the mailbox, right? Someone had to send it. And this leads us to the formal concept, which is called a consistent cut. It's basically a snapshot that respects causality, that respects the arrow of time. If an event is in our picture, then every single event that caused it has to be in the picture too. This is our guarantee that the snapshot represents a real, valid state the system could have actually passed through. So how do we get one of these consistent cuts? The answer is this really elegant and, honestly, brilliant solution called the Lamport algorithm. It's an amazing way to capture one of these valid snapshots without ever having to pause or stop the application. It lets us peek into the past without disrupting the present at all.
The magic trick behind this whole algorithm is a special kind of message called a marker. You could think of it like a wave of colored dye spreading through the system. This marker acts as a divider. Everything that happens before the wave is the past we want to capture, and everything that happens after it is the future.
The whole thing unfolds in 3 key steps. First, you've got the initiator. Some computer just decides to kick things off. It records its own state right then and there, and then it sends a marker message out on all its communication channels. Step 2, receiving the first marker. When another computer gets a marker for the very first time, that's its signal. It immediately records its own state, and then it forwards that marker out on all of its channels, continuing the wave. And finally, step 3, what if a computer that's already recorded its state gets another marker on a different channel? Well, then it knows to record all the messages that arrived on that channel after it saved its own state, but before this new marker showed up. These are the messages that were in flight during our snapshot. Okay, so that's the how. But what's the why? What good is this carefully constructed picture of the past? Well, it turns out it lets us reliably detect certain kinds of truths about the system, things we call stable properties.
So what's a stable property? It's a condition that, once it becomes true, can never become false again. It's an irreversible state. Think of it like a glass shattering on the floor. Once it's shattered, it stays shattered. You can't unshatter it.
A system-wide deadlock is the perfect example of a stable property. Once all those processes are stuck waiting on each other in a big cycle, they're going to stay stuck. Same goes for termination. Once a computation is finished, it's finished for good.
But on the other hand, something like, the message queue has 10 items, that's a transient property. It can go up, it can go down. These snapshots are designed to find those big, stable truths, not these fleeting moments. So how do we actually use this? Well, let's look at two huge applications. For deadlock detection, our snapshot gives us a valid wait-for-graph of the system. If we look at that graph and find a cycle, we know for a fact the system is deadlocked. For termination detection, we use the snapshot to check two simple things. Are all the processes idle, and are all the communication channels totally empty? If the answer is yes to both, we know the whole job is done.
And that right there is the big takeaway. The Chandy-Lamport algorithm gives us an incredibly powerful tool. It lets us impose a little bit of order on the absolute chaos of a distributed system. It lets us capture a moment in time that actually makes sense. A moment that lets us reliably spot these critical, irreversible states that are otherwise completely impossible to see.
And that leaves us with a really fascinating question to chew on. We've just figured out how to reliably look into the past of a complex, globe-spanning system. So what does that unlock for the future? How can we use this power of observation to build systems that are more resilient, more efficient, maybe even more intelligent? It's something to think about. Thanks so much for watching.